Let's consider this problem. A baker has 60 pounds of flour, 132 pounds of sugar, and 102 boxes of raisins. We have the requirements given for flour, sugar, and raisins for a batch of raisin bread and for a batch of raisin cakes. We also know that the profit is $30 for a batch of the bread and $40 for a batch of the raisin cake. We want to determine how many batches of each should be baked in order to maximize profit. So the first thing we need to do is decide what our variables are going to represent. So we are going to let x represent the number of batches of raisin bread and y is going to be the number of batches of raisin cakes. Okay, now we need to write our linear programming problem. We want to maximize profit. I'll call it P. How much profit are we going to have? Well, we have $30 for each batch of raisin bread. So we have 30 times the number of batches. That'll be 30x. We're going to add to it 40 times the number of batches of raisin cakes. So that'll be 40y. This will be our total profit. Now we have our constraints. Here we are limited by the amount of ingredients that are on hand. Okay, so if we look at the flour requirements, we know that the total amount of flour that we use cannot exceed 60 pounds. So we're going to use 1 per batch of the bread, so that'll be 1x. And then we're going to use, for the cakes, it'll be 2 pounds per batch, so that'll be 2 times the number of batches of cakes, so that'll be 1x plus 2y. This cannot exceed 60, so it's okay for it to be less than 60. We just have some leftover flour to be used later, but it cannot make more than 60. We cannot use more than 60 pounds of flour because that is all that we have on hand. Make sure you write your subject to on your constraints. Okay, that one was for flour. Okay, now we can have 1 for sugar. And we'll also have 1 for raisins. Okay, so for sugar we are limited to 132 pounds. That's the most that we can possibly use. 1 pound times the number of batches of bread, so that'll be 1x. Then it takes 4 pounds to make the cakes, so 4y. What about raisins? Raisin bread needs 2 boxes times the number of batches, so that'll be 2x. And then 1y, because it only takes 1 box for each batch of raisin cakes. This total cannot exceed 102. Once again, it's okay to be smaller than 102. That would mean we have some raisins left over, but we can't have more than 102. Does it make sense for x and y, either of them, to be negative? No, because they represent numbers of batches. So that gives us our non-negative constraints. And when we look at all this in a group, we realize that we have a standard maximization problem. So we can use the Simplex method. Okay, so the first thing that we want to do is write our initial system with our slack variables. We're going to put the constraints first. So here I have x plus 2y plus slack variable number 1 is equal to 60. Second constraint, x plus 4y plus slack variable number 2 is equal to 132. third constraint, 2x plus y plus my third slack variable gives me 102. Now I go back to my objective function, subtract everything so that everything is on the left side. So that gives me negative 30x, negative 40y, plus p, sorry, should have left more space, is equal to 0. And of course, all of our variables, including the slacks, have to be non-negative. That's our initial system, which we will use to write our initial simplex tableau. So I write the coefficients of x first, and then y. And now S1, so that'll be a 1, and then everything else zeros. S2, 0, 1, 0, 0. S3, I'll have the 1 in the third row. P, 0, 0, 1. Then my right-hand side, I have 60, 132, 102, and 0. This is my initial simplex tableau. So now we look for the most negative on the bottom row, and that's this negative 40. And so that gives me my pivot column. Now I calculate quotients. So 60 over 2 gives me 30 for the first row. 132 over 4 gives me 33 for the second row. Third row, I get 102 over 1, which is 102. So the smallest will be that first row. That's my pivot row. So then here's my pivot element. So I do row operations either by hand or using my technology to get a 1 in that position and zeros elsewhere in the column. When I do that, here's what I get. First row, 1/2, 1, 1/2, 0, 0, 0, and 30. Second row, negative 1, 0, negative 2, 1, 0, 0, and then 12. Third row, 3 halves, 0, negative 1/2, 0, 1, 0, and then 72, and then negative 10, 0, 20, 0, 0, 1, 1,200. Okay, we look now to see if we have any negative numbers on the bottom row. We do right here. So there's my pivot column. Now I calculate quotients using any positive numbers in that pivot column. That first row I will get 30 over 1/2, which is 60. For the next one, remember you do not calculate quotients for negative numbers in the pivot column. So I'm just going to simply note that that was a negative number. I'm not going to compute a quotient. Then for the last one, I have 72 over 3 halves, which is 144 over 3, which is 48. Remember, we do not calculate a quotient for the bottom row because that will never be our pivot row. This one is the smallest, so that gives me my pivot row. So this 3 halves is my pivot element. And I do my row operations either by hand or using technology to get the next matrix. Here's what we get. So my first row, 0, 1, 2/3, 0, negative 1/3, 0, and 6. Second row, 0, 0, negative 7/3, 1, 2/3, 0, 60. Third row, 1, 0, negative 1/3, 0, 2/3, 0, and 48. There's that smallest quotient popping up. And then in my last row, my objective function row, I have 0, 0, 50 over 3, 0, 20 over 3, 1, and then 1,680. Okay, I notice that I do not have any more negatives on the bottom row. So that means I am done pivoting and I have reached the optimal solution. So I just need to write it down and figure out what it means. Okay, so my non-basic variables, these are the ones that are being set equal to 0. These are the ones with the junk in the column. So what are they? S1, junk in the column, so that gives me S1 equals 0, and S3 equals 0. Then my basic variables. Okay, these are the variables that have 1 and zeros in the column. Let's write down what they are. So x, so we find the x. This is from row 3. Here's my x. Here's the 1 in the x column. What's that equal to? 0. This one's non-basic set equal to 0, 0. Non-basic set equal to 0. So all I end up with is 1x equals 48. So I have x equals 48. For my second column, my y, there the one appears in the first row, so the value's in the right hand side of the first row, so y is equal to 6. What else do I have? S2 is equal to 60. S2 is equal to 60, and then P is equal to 1,680. So now we want to write our final answer, which had to do with how many batches of each the baker should bake. The baker should bake, okay, X represented the number of batches of raisin bread, so 48 batches of raisin bread. And 6, that's the Y, batches of raisin cake. And and that will give us a maximum profit of $1,680. Wow, that's making me hungry. Keep in mind what the slack variables mean, even though it didn't ask us to answer this in the original question. If you were doing this as a businessman, you might need to know S1 represented the number of pounds of flour that was on hand, so that means we have 0 pounds of flour left over. S3 came from the constraint involving the raisins, so that means we have 0 boxes of raisins left over. S2 equals 60 down here. That means we have 60 pounds of sugar that did not get used in this particular set of batches. Okay, I hope this helped you to understand how to use the Simplex method to solve problems. Good luck, and I will see you